There we go. I don't know why I keep forgetting. Okay, so let's take a look at, not to keep this open too. Let's take a look at this other one. There we go. Okay, so 2 CO2 plus 2 C2H5OH goes to C6H12O6. And again, they want you to find delta H. Okay. All right, so in the one that they give us at the top, C6H12O6 is a reactant. In this one, it's a product. So that means they reversed it. And so again, if you reverse it, you got to change the sign. The original delta H was negative. Since we reversed it, it's got to be a positive. Okay. And then you look at the numbers. In front of the glucose, originally it was a 1. Here it's just a 1. It's still a 1. It hasn't changed at all. So if it hasn't changed at all, you just multiply by 1, or you don't multiply by anything, really. So that means it's going to be the same number. So 69. Okay. So if the equation is just the reversal of the original one, you just change the sign. If it's the reversal and you multiply it by something, then you just do 2 steps. You change the sign and then you multiply by that number. Okay.
Thank you very much.
Good. Absolutely. I'm glad you asked that one. Okay. Any other questions, anybody? Okay. All right. So what I'm going to do now is I'm going to talk about a little bit more about calorimetry. We looked at calorimetry yesterday. But what I'm going to show you is one where it puts everything kind of together here. So this one we might call solving a basic calorimetry problem. Okay. So here's the picture. We have an insulated cup. So like a styrofoam cup or a thermos or something like that. And inside it has water. Okay, so there's water in here. There is also a thermometer to measure the temperature. And then there's a sample. Okay, this has got to be insulated. Because what happens is if you don't insulate it, I'll call it insulator. If you don't insulate it, the heat can transfer so quickly that the temperature doesn't change as rapid or as well as it could. So here's the idea. A 59.6 gram sample of iron, okay, is put into the water. Okay. The iron sample starts off at 96.6 degrees C. The water starts off at 24 degrees C. Okay. When the water stops changing, stops changing, the temperature is 26.6 degrees C. Okay. It does tell us that the pressure remains constant at 1 atmosphere. And then it says calculate the specific heat capacity of the iron. And then round to 2 sig digits. All right, so this is a calorimetry problem. And what we have to add in this particular problem is that the iron starts off very hot, right? It's 96.6 degrees C. The water is much colder. It's at 24 degrees C, which is around room temperature. Remember we said that heat flows from the hotter object to the colder object. So heat is going to flow from the iron. It's going to go from the iron into the water. So the water will get hotter and the iron will get colder. Okay. In a sense, we're thinking of the iron as the system. So let's take a look at how we go about this. With this one, what we have to do is we have to say the following. There is an equation we use for heat flow. And the equation is Q, heat, is equal to mass times specific heat capacity times the change in temperature, where the change in temperature is T2 minus T1. Right? That's essentially called the calorimetry equation. But here's the issue here. There's two materials in which heat is flowing. You got the iron and you got the water. There's two materials. So how do we deal with two materials? How do we calculate the heat flow if there's two materials? And here's what we say. The heat that goes out of the iron, okay, remember, heat's going to flow out of the iron because the iron is hotter, is going to go into the water. Actually, let me draw this a little bit differently. Let me label it a little bit differently. So this is the iron, this is the water. Heat is going to flow from, again, the hotter object to the colder object. So how do we deal with that in terms of a calculation? The way we deal with it is we write mc delta T for both of them. But since the heat that's coming out of the iron should be the same as the heat that's going into the water. Think about it this way, right? This thing is like giving off heat into the water. The water is what's going to get hotter. So these two heats are equal to each other. So I'm going to label it this way. Heat of the iron is equal to heat of the water with one issue. The sign is different. Okay, that's an important issue, right? If heat comes in, that's positive. If heat goes out, it's negative. So here's the way this is dealt with mathematically. Q iron plus Q water equals 0. Okay, this is the equation essentially you want to start with. I'm not drawing very nice Q's. Let me write that a little different. Okay, so this is a little bit different than this one, right? This is not taking the sign into account here. So there's an error in saying this. It's true the amount of heat that comes out of the iron is equal to the amount that goes into the water. That's true. But they're different in terms of their signs because one is increasing and the other one is decreasing. So this is the more appropriate equation to use right here. So then what you do is you say, wait a minute, this is the mass, M is the mass, C is the specific heat, and delta T is the change in temperature. So what I'm going to do, let me save this one, is I'm going to write out mc delta T for both. I'm going to do it for the iron, and I'm going to do it for the water. Okay, and then what I'm going to do is I'm going to say that mc delta T of the iron plus mc delta T of the water, that's got to equal 0 because, again, we said that Q of the iron plus Q of the water equals 0. Okay, so let's put in the numbers. For the iron, the mass is 59.6 grams. We don't know the specific heat of the iron. That's what the question is. What is the specific heat of the iron? So I'm just going to write C for specific heat of the iron. And then delta T for the iron, that's the final temperature, which is 26.6 minus the initial, which is 96.6. Okay, so this is mc delta T for the iron. Okay, and then we're going to do the same thing for the water. For the water, it's the mass of the water, which was 200 grams.
I thought the problem said that 96.6 was, no, 26.6 was the final temperature of the water, not the final temperature
Yes,
of
it
the iron.
did. But let me go back to the picture. Take a look at this picture. The iron is in the water. So when the water reaches 26.6, the iron will also be at 26.6. They'll be at the same temperature because they're in the same mixture together, right? So at the end, the water will be at 26.6, but so will the iron. Okay. That's called thermal equilibrium, when two things come to the same temperature.
So we can always assume that at the end of the experiment, they have reached equilibrium. They're
That's
not
right.
measuring.
Yeah, exactly. If they're in thermal contact, meaning they're in the same space, at the end they should be at the same temperature, right? Imagine if you have two rooms, one is air conditioned and one is heated, but then you open up all the doors in between the two rooms. Eventually, they will be at the same temperature. Okay. So the mass of the water is 200 grams. The specific heat of water, that was the number we went over yesterday. Specific heat for water is 4.184. And then the change in temperature of the water started off at 24 and it ended at 26. Okay, so this would be mc delta T for the water. Okay, and what we said was those two terms, when you add them together, they got to equal 0. All right, so I'm going to go through the calculation.
So we can assume that the mass of the water is always the same as the mass of the sample?
No, the water here it says was 200 grams.
Oh, I'm sorry.
And then I may not have written that down. I'm looking back and I may not have told you that.
No, you're right. I'm
It's
just
actually
sleeping.
given. Okay.
I
So the
apologize.
water's 200 and then the iron is 59.6. Okay. So here's what happens when I do the first one. When I take the 59.6 times the delta T, we don't know what C is, so I'm just going to put in C. I get minus 4172. So I'm going to put that in parentheses. And then I don't know what C is, so that's right there. Okay, I left the units out for this because the units, we'll go over the units after I do the number. So what I did was I took the 26.6 and I subtracted 96.6. That gave me minus 70, right? Because it's the final minus the initial. The final was 26.6. The initial was 96.6. That's minus 70. And then the mass was 59.6. So when we multiply those two numbers together, you get minus 4172. Again, we don't know what C is, so I'm just going to leave it as C. Now on the water, we know all the numbers, so we don't need any C in there. We can just calculate the whole thing. So 26.6 minus 24 is only 2.6. But we're going to multiply that by 4.184, and we're going to multiply that by 200. And you get 2175.68. And then those two you add together, and you get 0, right? Because again, the idea here is the heat coming out of the iron is going into the water. So Q of the iron plus Q of the water equals 0. So this is Q of the iron. This is Q of the water. Those two added together should be equal to 0. Okay. Again, the question was, what's the specific heat capacity of the iron? So they're just asking us for what C is. That's the only number that they didn't give us. By the way, you could look it up in a table. The specific heat of iron, I think, is around, it's either 0.44 or it's 0.56. It's somewhere around there. So let's take a look. How do we deal with this mathematically? Well, there's a couple of things you could do algebraically. Essentially, what you have is a number. So let me make this simple. Suppose I had 3C plus 2 equals 0, just to make the numbers easy. And you wanted to find out what C was. Okay. What you would do is you could subtract 2 from both sides. Right? And if you subtract the 2 from both sides, plus 2 minus 2 is 0. So you would have 3C equals 0 minus 2, which is just minus 2. And then you could divide both sides by 3. And so 3 divided by 3 is 1, so you'd have C, and then you'd have minus 2/3. Okay, so for that algebra, there's 2 steps. One would be to subtract one of the terms and then to divide by what's called the coefficient. This is called a coefficient here. So let's try that. I'll write the numbers down here again. Minus 4172C plus 2175.68 equals 0. So let's subtract 2175.68 from both sides. So that's going to give you 0 right there. So now you'll just have minus 4172C equals 0 minus. So that would just be minus 2175.68. Then in the second step, we could divide both sides by the coefficient, which is minus 4172. Okay, minus 4172 divided by minus 4172 is 1. So you just have C equals minus 2175.68 over minus 4172. And it looks like it's going to be around a half. It might be 0.44. Let's see, 2175.68 divided by 4172. That's about 0.52. Okay. 0.52. They said 2 significant digits, so I'm just going to stop at 0.52. Okay. Now, I didn't show the units throughout the entire process, so let me just show them to you separately just so you can see where they come from. This should be in joules per gram degree C, because that's the units of specific heat. So I'm going to come back all the way up here, but I'm just going to show you the units. The mass is in grams. We don't know what C is, so I'm just going to put C. The change in temperature should be degrees C. And then we're going to add to that grams, joules per gram degrees C. And then the change in temperature is degrees C. Okay. The first step we did algebraically was we took this second term, this 2175.68, and we subtracted it from both sides. So that means we'll have grams times C times degree C equals grams times joules per gram degree C times degree C. And then what we have to do to get C, the specific heat, is divide both sides by grams. Right, we divide both sides by grams and divide both sides by degrees C. And so the grams will cancel, the degrees C will cancel, and you'll be left with joules per gram degrees C, okay? So temperature is typically in degrees C. Mass is typically in grams. And then the specific heat capacity is typically in joules per gram degrees C. Those are the units that you'll see for these types of problems, okay? A point out about specific heat capacity when you do these problems, just so you can kind of check your answer, evaluate your answer. Specific heat capacity for metals, it's going to be between 0.1 and 1 joules per gram degrees C. So if it's iron and you get a value greater than 1 or less than 0.1, that's an indication that something went wrong in your calculation, okay? So most metals are 0.2, 0.3, 0.4, 0.5, somewhere around there. Water is unusual in that it has an enormous specific heat capacity. 4.184 is much larger than 0.2 or 0.3. Water has a very large specific heat capacity, and that is important in terms of its physical properties, that it can absorb so much heat without changing its temperature very much, okay? So that's just a little check. So if you're doing a problem, now if they tell you it's an unknown object and they don't tell you it's a metal, then it's kind of hard to evaluate what your answer is because of, you know, but again, you know, the highest value you're ever going to see is for water. Water is 4.184. So if you get a value of specific heat capacity that's 10, that's an indication there's something wrong with the calculation. So typically they're between 0.1 and 1 for metals, and then for water it'd be as high as 4. Okay, so there you go. And that right there is essentially that's a culmination. That's like a calculation that takes in essentially everything that we've learned about calorimetry, the direction of the heat flowing from hot to cold, the idea that one material absorbs all the heat from the other. That's all taken into account. And then, of course, the equation MC delta T is used in there. And again, just to remind you, if you're using the textbook, they're going to use a slightly different symbols for this type of problem. So they might use this one for specific heat capacity. And so they put the S in front of the M instead of the M in front of the S. Okay. Good. Any questions on that one? Just looking through it, there's one more thing I wanted to mention about units. This might confuse you if you haven't seen it before. So sometimes units can be written using a division sign. So this would be the units of specific heat. So what we're saying is we're taking joules and we're dividing it by grams, and then we're also dividing it by degrees C. But sometimes it can be written this way, as instead of division, as multiplication. Okay, so the notation here looks quite a bit different, but it's essentially the same. And what we're doing is we're saying the following. we're using exponents. If I write 1 over x, that's equal to x to the minus 1. So if I write 1 over grams, that can be written as grams to the minus 1. If I do 1 over degrees C, that can be written as degrees C to the minus 1. So for that reason, joules over grams over degrees C can be written as joules times grams to the minus 1 times degrees C to the minus 1. So you may see that symbology used for the units when you do these problems. Okay. Okay, so what I want to do now is I want to talk a little bit about what's called standard formation. And this is related to delta H. Remember, delta H is our energy. So this is enthalpy change. Here's what happens. If I do the following, if I react, let's say 1 mole of gaseous hydrogen, so this is 1 mole, right? The coefficient, will use that as the number of moles. So if it says a 1, that means 1 mole. And a half of a mole of gaseous oxygen to form 1 mole of water. It turns out if you do this experiment, what you get is delta H is minus 286 kilojoules per mole. Okay. If I change the state of matter, so if all I do is make it gaseous water instead of liquid water, it turns out that changes delta H. Right, so all I did was change this from a liquid to a gas, and it actually changes the value of delta H. Okay. The other thing I could do is I could say, well, suppose I wanted to not have fractions, so I'm going to multiply the equation by 2. So it's still the same states of matter, still the same materials. We just multiplied by 2. What we learned with enthalpy is then that would be minus 484. You would multiply that by 2, right? So what that tells us is that the states of matter and what the coefficients are in the equation affect what the enthalpy change is, what delta H is. Delta H is affected by the coefficients, and it's affected by what states of matter we have. So for that reason, what we want to do is we want to have what are called standards. And these standards are values of delta H that can be predicted from the equation. So one of the steps that we want to do in terms of understanding or being able to accomplish this is to write a balanced equation for the formation of a compound. From its elements. Okay, so I'm going to show you an example of how we go about that. The first one we're going to do is acetic acid, which is, I'm going to write the chemical formula like this: HCH3CO2. Okay, let me show you the structure of acetic acid just so you can see it, because I know you're doing a titration experiment this week. So acetic acid is an acid. It's a weak acid. It's in vinegar. And it's the acid that gives vinegar its sour taste. Okay. Vinegar has one hydrogen that's acidic, meaning that if you take the whole molecule and analyze it, there's only one hydrogen that will react with a base. And that's this one over here. It's attached to the oxygen. So that hydrogen can be transferred. So if I took, for example, let me draw it again. If I took a hydroxide ion, so here's hydroxide, what would happen is the acetic acid would transfer the H plus to the hydroxide ion. And so then you would get the hydroxide ion would become water. And then the acetic acid would be called acetate. This is called acetate. Okay. So it's an acid, and this is the acidic hydrogen that's on that acid. So what we want to do in this type of exercise is we want to write the equation, chemical equation for the formation of the acetic acid. And all we're going to start off with is the chemical formula of the compound. There we go. So that's just one way of writing the formula. Okay. So how do we do this? What you do is you start with an element. So first you look at what elements are in there. So you see there's hydrogen. You see there's carbons in there, right? There's also carbon. And then there's oxygen. There's 3 elements in that compound. Okay. The general format is you take the element, so I'll call it element 1. You add it to element 2. You add it to element 3. And then you write an arrow to form the compound. And the coefficient in front of the compound should be a 1. So it's got to be balanced. And then you get your compound. So that's what this exercise is asking you to do. It's asking you to write a balanced equation for the formation of 1 mole of that compound, the acetic acid. So here's how you do it. The first element is hydrogen. But remember, hydrogen is one of the 7 elements that are diatomic. So I'm going to write the diatomic elements again. Those are the ones that are diatomics. So when you write diatomic elements, I mean, when you have an element that is diatomic, you got to write it as diatomic. So it's H2. So for H, we would put H2. Carbon is not one of the diatomics. It's not in there, right? So we can just write C. The next one is oxygen. That's a diatomic. So we write O2. Then we write the arrow. And then we write the formula for the compound. Okay. It says in this problem, I'm sorry I didn't write it in here, it says it's liquid. Liquid acetic acid. So I'm going to write L here. Okay. We'll go over the states of matter in a moment, but first let's balance it. To balance it, we notice we've got 1 hydrogen here plus another 3, so that's 4 hydrogens. Here there's only 2, so I'm going to put a 2 in front of it, and that'll give us 4 hydrogens. Over here we've got 2 carbons, so I'll put a 2 in front of that one. And there's 2 oxygens. Well, there's already 2 here, so we're set there. Okay, so we've got the balanced equation. the last step is to say, okay, what are the states of matter? And those are things that you may not have much experience with, but I'm going to give them to you right here. Hydrogen, nitrogen, oxygen, fluorine, chlorine. These are all gases at room temperature. Bromine is a liquid, and iodine is a solid. Okay. The carbon is also a solid. So we would put G, S, and G, and then they told us it's liquid acetic acid, so we would already have that one. Okay. So these ones, you might want to memorize those. Those ones, or write them down somewhere. Those ones are gases. Bromine is a liquid. Iodine is a solid. And then carbon is also, if it's a metal, it's also a solid. So metals are solids. And that should get you through most of them. So let me see if there's another one here I can show you. Yeah, let's try one more. Write a balanced equation for the standard formation reaction of Fe2O3. Okay. So let's try like this one only has 2 elements. So again, the idea is you're going to identify the 2 elements, or 3. In this one's case, it's only 2. So you've got iron. That's the first element. Oxygen is the second element, but remember, oxygen is a diatomic, so we write it as O2. Then arrow, and then the compound, Fe2O3. It actually says, I'm sorry, I forgot to put in here, it says it's solid Fe2O3. So that's solid. Okay. Now, let's do the states of matter and then we'll balance it. This is a metal. Metals are solid. Oxygen's a gas. Okay, so we got the states of matter. Now we got to balance it. Now be careful. When you balance it, this has to be a 1. It can't be a 2 or a 3 or a 4. It's got to be a 1. So that means you may need to use fractions when you balance the equation. So let's come over here. We've got 2 irons. So I'm going to put 2 irons over here. So the iron is balanced. Now we have 3 oxygens here, but we only have 2. So you're going to have to use a fraction. So here's what I'm going to do. I'm going to write an X here. And let's figure out how to deal with this. The total number of oxygens on the left side is X times 2, right? This times that. That's got to equal 3. So to figure out what X is, you just divide by 2. So it's 3/2. So that means it's going to be 2 Fe solid plus 3/2 O2 gas Fe2O3 solid. And that would be the equation for the standard formation of iron 3 oxide, which is Fe2O3. This is the equation for the standard formation of Fe2O3. Remember, it's got to be 1 mole. So that means sometimes you got to have a fraction on the left side. States of matter, metals or solids, oxygen, hydrogen, nitrogen, chlorine and fluorine. Those ones are gases. Okay. Okay. So now the reason that we go over that is because it turns out the delta H values for those types of equations are used in the Alex data tab. When you go through the Alex data tab, you're going to be able to look up standard heats of formation. And the symbol we're going to use for that is delta H. F for formation is a little subscript. So that's right there. And then the term standard, we represent that with a little symbol, which is a degree sign. So the standard is indicated with the degree sign there. So we can look these up in the data tab to do a certain type of calculation. And here's the calculation we'll do. We're going to find the heat of reaction from the standard heats of formation. Okay. So let me look up some values for you, and then we'll take a look at these. So when you look up in the Alex data tab, it's going to give you the numbers for different materials. So for example, O2 is 0. CO2 is minus 394. H2O liquid is minus 286. H2O gas is minus 242. CH4 minus 75. These are the delta H of formation, standard, and then this is the material. There's many other materials in there, but these are some of them that are in that data table. So here's how you go about this. The standard problem is this. They give you a balanced equation. Oops, I forgot to not put a 2 there. It's just 1. So they give you a balanced equation. Typically, the ones you're going to do are combustion. And then they ask you to figure out what delta H is. Okay, so they give you a balanced equation and find delta H. What you're going to do is you're going to use the numbers that are in the data tab. Okay, you can look those up and click on them to figure out what they are. So you're going to use those. And then you're going to use a formula, a mathematical formula. And here's the formula. Delta H of the reaction is equal to the sum, right? Sigma is the mathematical symbol for adding things together. The sum of the number of moles of a product times the standard enthalpy of formation of that product minus the sum of the number of moles of a reactant times the standard heat of formation of that reactant. So the formula looks a little scary perhaps, but it's really easy to use. Here's how you go about it. You take your balanced equation and you identify the coefficients. Here's a 1 and a 2. These are the products. So you take the coefficient, which is N product, and multiply by the heat of formation that's in the table here. There's your heat of formation for CO2. And you add up all the products. N times delta H for all the products. You add them up. Then you do the same thing for the reactants. You add up N times delta H for the reactants. And then you subtract the difference. So you take products minus reactants. Okay? So let me show you how we go about this one. We're going to do the products. I'll do the products first and then the reactants and then take the difference. So in the equation, you got 1 mole of CO2, so 1. CO2 is minus 394. The second product is water. You got a 2, and water is negative 286. Okay? Add those together. So N times delta H for each product, add them up. So 394 negative, remember it's got a negative number in there, plus 2 times 286 negative, and you get minus 966. Do the same thing for the reactants. N times delta H. So the reactants, there's a 1. CH4 is right here, negative 75. You got 2 for the oxygen, so 2. But oxygen is 0, so you can just put in a 0 there. That makes that easy. So you get minus 75. Okay. So N times delta H, you're looking those delta H up values from the table. Okay. The balanced equation is going to be given in this particular problem. So then you take products minus reactants. So the products was minus 966. The only thing that's tricky about this is that you're going to be subtracting negative numbers, and that can be kind of confusing. So subtract minus 75. If you subtract a negative number, that's like adding a positive. So it's really the same as minus 966 plus 75. Okay. So 966 negative plus 75, and you get minus 891. So that means our delta H for this reaction right here is minus 891 for the whole reaction. And that's the power of this. That's why these two topics are in here, writing the balanced equation and then being able to use this, is that now we can look up delta H values for all the materials and then plot them into this formula and figure out what delta H for a reaction is given. It allows us to predict delta H for reactions we haven't seen before. Okay, so let me show you another example. I think most of these are combustion. Here we go. So I'm going to give you the balanced equation, 2C2H6 gas plus 7O2 gas, 4CO2 gas, 6H2O liquid. Now again, what the question is what's delta H for this? Okay. It also says use the information in the Alex data tab. So right there, that's telling you you're going to look up these values. Okay. So if you look them up in the data tab, what you'll find is that this is minus 87. This one's 0. So I'm looking them up. Minus 394, minus 286. So I've looked those values up. Now we're going to use that equation. Delta H of reaction is the sum of the number of moles of the product times delta H of formation of the product minus number of moles of reactant, delta H of formation of the reactant. So I'm going to do products first. Remember, it's very simple. It's just N times delta H. You look up the delta H values. So let's do the products first. So 4 times minus 394, 6 times minus 286. So you add the products together. So let's see what that comes out to. 4 times 394 plus 6 times 286. And I get minus 3292. Okay, now you do the reactants. First reactants right here, there's a 2. 2 times minus 87. 7. But this one's oxygen, so it's 0. So it looks like you get minus 174. And then you do products minus reactants. Right? Products minus reactants. So that would be minus 3292. That's the products. Minus the reactants is already negative. So minus 174. Products minus reactants. So 3292 is negative. Oops. 3292 is negative. Minus a minus. So that's plus. And you get minus 3118. So what we would say here is that the standard heat of formation, heat of reaction for this reaction is minus 3118 kilojoules per mole. Okay. And there you go. And those are pretty much the end of chapter 5. So what we did was we looked at an introduction to what energy is, kinetic energy. We then looked at heat. We then looked at work. We then looked at enthalpy. We then looked at calorimetry. And then finally, we looked at this idea of standard heats of formation. So there are available big tables, page after page after page, of each compound that's ever been made and what its heat of formation is, its delta H is. So these values that I looked up here for C2H6, O2, and CO2 and H2O, there are literally thousands of values for different materials. So now any reaction you look at, you can just plug those delta H values into that equation, into that formula, and you can figure out what the heat of reaction is for any kind of reaction. Okay. Not all reactions, but quite a large number of them, probably tens of thousands of them. Okay. All right. So that's chapter 5. I hope you have a good end of the week. Reach out to me this week or this weekend if you have any questions. And I'm going through, some of you have already taken exam 2, so I'm going through and regrading exam 2. So that should be popping up soon. And I did grade the second laboratory report. So that should be in your ALEX scores by now as well. Okay. Have a wonderful day and a wonderful weekend, you guys. And again, reach out to me if you have any questions. Okay.
Have a wonderful day.
Thank you very much.
Thank you.
Bye. Thank you.
Bye-bye.